we are going to solve count all valid pickup and delivery options today. Here we are given n orders. Each order consists in pickup and delivery services. Count all valid pickup delivery possible sequences such that delivery is always after pickup. Okay, we have to mod it. So basically we are given integer n, and that means how many pickups or deliveries are there. So n equal to 1 means there are one pickup, and so we have to deliver that thing. So this is a sequence, valid sequence. What if there are two? 2 means there will be two pickups and two deliveries. P1 means pickup for number one item, D1 means delivery for number one item. So this is a valid sequence, this is so there we can see that there are 6 possible sequences. But what's an invalid sequence? So P1, D2, P2, D1, this is an invalid sequence. Because why? Because D2 comes before P2. So you are processing something later but delivering it earlier. This cannot happen. So delivery must follow its pickup. If we generalize this thing, it means for any nth pickup, if we are going to deliver it at any time, like we are going to deliver it, Pn must, this one must come before Dn. Okay, Pn must come before Dn. Pn cannot follow Dn. So this is a rule. Just seeing this problem, we can give we can see that this is a dynamic programming problem basically. So when n equal to 1, what we're doing is we have only one sequence, P1 and D1, and nothing else is there. Given this idea, how can we solve for n equal to 2? So this is very straightforward actually. Look at this sequence, just look closely. This is P1 and it is followed by delivery for that product. How can we construct for n equal to 2? N equal to 2 means there will be another process, P2. Okay, and we know that D2 will follow P2. D2 comes after P2. How can we construct for n equal to 2 from this sequence? Think about it. We can place P2 in certain slots. We can place P2 here, we can place P2 here, we can place P2 here. Okay, now think for the first case. What if we place P2 here? If we place P2 here, we can place D2 here. For P2 here, we can place D2 here, we can place D2 here, we can place D2 here. Okay, so we can see that for this position we have this position for D2, this position for D2, and this position for D2. Okay, so this means for previous solution n equal to 1, there are two items P1 and D1, and if we choose this position for P2, we can put D2 in this place, this place, this place. How many places are there? This is actually the number of empty spaces in this arrangement, P1 D1 arrangement. How many empty spaces are there? 1, 2, 3. Actually, in the previous sequence, if there are if there are total items are 2, previous sequence has total 2 items, number of empty spaces are actually 3, which is 2 plus 1. Okay, we can put D2 in these 3 spaces if we place P2 at the very beginning. Okay, so this arrangement is fine, completely fine. Now what if we place P2 here after P1? If we place P2 here, D1 is here, the number of spaces for D2 must come after P2. So D2 can be placed here, D2 can be placed here. So number of empty spaces has been reduced to, there was 3 spaces before, now there are 2 spaces. We have lost 1 space, that was before P1. Okay, this space cannot be used for D2. You can see, because D2 must come after P2. Then what if we place P1, D1, P2 at the very end? How many spaces now are there? There are only 1 space. So if we count this total, it comes like 3, 2, 1. This is 6. This is the answer for n equal to 2. Okay. Now we are going to solve for n equal to 3. Let me get this all sequences here. Okay. These are all the sequences for n equal to 2. Now we're going to construct for n equal to 3. Now take any sequence. All of these sequences are valid. I'm going to take this one. P1, P2, D1, D2. I know this sequence already. Now I am going to solve for n equal to 3. Where can we place the process 3 or P3? We can place it here. Let color it with different color. P3 is here. Okay. If we place P3 here, we now need to place D3. Where can we place D3? We can place D3 here, or we can place D3 here, or we can place D3 here, here, here. How many empty spaces are there? 1, 2, 3, 4. 4 plus 1, 5. 5 empty spaces. If we place P3 in this position, there are 5 possible ways to place D3. 5 different ways. So all those different ways are valid. Okay. But we have solved this for one. You can see that we have solved this for one sequence only, right? In this same way, you can place P3 in the first position for all of these ways. Yes, you can solve for all of these ways. Like if we place it here, P1, P2, D2, D1, and now we need to place P3. Same way, you place P3 here, and you can place D3 in 1, 2, 3, 4, 5 positions. You can see that. So if we place P3 at the beginning, we can place D3 in 5 positions, and this can go for all of these sequences. Okay, so if we place P3 at the very beginning, we can get total 5 into this previous number of sequences times. Okay, previous sequence. How many sequences were there? Okay, so these are total ways in which you can place P3 at the beginning at any of the sequences. Then if we place P3 after P1 in this position, this is P3, we can place D3 in this position, this position, this position, this position. So there are like 4 ways, 4 times previous number of sequences. Okay. And this will go on actually. So we can see that there is a pattern like 5 plus 4 plus 3 plus 2 plus 1. Yeah, if we place P3 in this position, there will be like 2 slots. In this position, 1 slot. This if we place P3 in this position, there will be like P3 in this position, 4 slots. 1, 2, 3, 4. Yeah, if we place P3 in this position, there will be like 3 slots. This position, 2 slots, and this position there will be only 1 slot. So our answer will be like this, like 5 into number of previous sequences. How many previous sequences are there? In this case, n equal to 2, there are 6 sequences, plus 4 into previous sequences, plus this. We can simplify this in one formula. Just what? Like 5 plus 4 plus 3 plus 2 plus 1 times previous sequence. number of previous sequences. If we apply this formula, we will solve it for n equal to 3. This is pretty much the idea. The code is very straightforward. We need to mod it, so I have taken a mod here. This is here, and for calculating the first n sum, this is a formula, you know, n into n plus 1 by 2. And for the very beginning, when there are no product or delivery, there was only there was like nothing. So I have calculated that how many ways you can do nothing. Equal to 0. How many ways you can do nothing? There are only one way. Nothing is the way. Okay. Then for n range 1 n plus 1, for every we are going to solve 1 by 1, and prevent means the previous what is the n value of the previous term, and preposition would be prev n into 2 plus 1. Why the twice? Because for n equal to 1, n equal to 1 means there will be one product, and how many items we needed to place? 2 items actually for n equal to 1, p1 t1. And how many empty slots are there? Empty slot, this is an empty slot before p1, after p1 an empty slot, after t1 an empty slot. So basically how many elements were there? Plus 1. That's the number of empty slots. So this is it, times 2 plus 1. Prep result would be get n sum prep positions. So this is three empty slots right there. So we have to calculate the sum. Why? For the first empty slot, if we place p2 in the first empty slot, what will happen? If we place p2 in the second empty slot, what will happen? That's why 2. If we place p2 in the last empty slot, what will happen? That's why it is 1. So we are taking the get all sum of previous positions, and we are multiplying it with previous result. How many sequences were there? Previous result means how many total sequences were there. So we have to multiply it with that. So after this, for nth item, we are getting the result here.